broadcast is now starting. All attendees are in listen-only mode.
Alright, and it's keeping track of the screen.
Yeah, looks, and it's keeping track of both screens right now. You can see the audio is finally working. You can hit that red arrow to close that, or not, or to like minimize that bar to the side.
Oh, okay.
Should be fine. So just double check we're getting audio.
Why is it on here twice? Ah. Oh, because one's the projection. Ah. Oh, that's weird. Okay.
All good.
So last time we kind of ran through some modeling stuff. We got stuck on. Oops. Well, we got stuck. Why? Oh. Why was this stuck? Okay. Where's PowerPoint now? Let's start it over. Okay, who wasn't here last week? Oh, okay. So last time we just kind of went over some of the basics of MODFLOW, how it works, and why we use it. Unable to record to the cloud.
That's fine. It'll save it to the computer and I'll rip it off later.
Okay.
So you coded a finite difference model yourself, correct?
Yes.
Okay, so it's kind of the same. MODFLOW is basically the same principle.
Yeah.
Of what you would have
It's
coded.
the USDS code.
Yeah.
So it's what we use here. So we just talked about some of the gridding issues, some of the running the model kind of things, where we're going. Okay, that's just for that. All right. And, kind of we need to start talking about the data that goes into it. So the point of what we're doing here is kind of several-fold, is to kind of see where we've come from to get the models that we have now, or how we got to the point where we're at now. And then we need a lot of discussion on where to go in the future. And so, we got lots of ideas and directions and stuff, but as we work together on various pieces and stuff to go forward, the modeling is going to get a lot more complicated as our computing power is increased. I'm going to say the old guys had it real simple and I had it simple because, it's, as you get more computing power, you can put more things into it. You can make it more sophisticated, more complicated, which of course makes everything harder. That's to take away nothing from the old guys. A lot of the things they did back with these electronic analog models and stuff, transmissivities are still valid. More valid than we might even give it credit for. And so we've evolved from, two-dimensional models to quasi three-dimensional models to more three-dimensional models. And so, and of course, principal to all that is the geology. And so we kind of need to discuss. So MODFLOW has a couple different, the different things you put into it: the rivers, the geology, the recharge, the drains, the pumpage. So there's all those different packages that have to go in there to make a model work, observation well data. Then, there's all sorts of decisions we need to make on how much of the geology to represent. How can we, what can we ignore? What do we have to put in? And what's important to what we're looking at. So, we might have on a regional basis fewer model layers, and then maybe we zoom into, a Crystal Lake problem, and we need to find this down, or we need, a contaminant problem or something that needs to be more specifically addressed. So let's see. So we were talking about that last time. I was talking about where we were resolution-wise on the left versus where higher resolution on the right. You can see things are a lot different. How the model works, yada, yada, yada. MODFLOW is modular, so basically you're creating. In the old days, you were writing an input file. I guess you still do, but for your different boundary conditions, your different geology, your hydraulic connectivity, your rivers, your drains, and your solver, and then there's all the coupled models that go on to it: MT3D, reactive transport, mod path, and there's a whole bunch of other things that have been added on, calibration codes, optimization codes, things like that. Oh. All right. I don't know what that was.
It was a PowerPoint update thing.
So this is where Daniel walked in and things ground to a halt. But we were talking about the process, and that's what's described in this textbook by Mary Anderson, who's a professor up in Wisconsin. There's a new version of that textbook out that Daniel is going to order a bunch of copies of.
I'm at least going to order one.
Okay.
We should discuss on the library, but that's another discussion.
Okay.
But we'll get a couple of them at least.
I mean, this is pretty standard. I mean, this is in the MODFLOW book as well. Where you pick out your conceptual model. Well, obviously the top box is the most important. And then we're going to talk today more about the conceptual model on the geology side. And then since you've written your own code, there's a whole lot that goes on here as far as, once you're choosing how you're going to model your system, is choosing the right code or creating your own code and validating that code. So MODFLOW itself, before Daniel came in, I just kind of blew by that and say, well, okay, MODFLOW's been around a long time. It's the industry standard, yada, yada, yada. But now that you have all these GUIs that interface and write the code for MODFLOW or actually make changes to the MODFLOW code, this is what Devin uses with time variant materials, we have to go back and look at that code selection and is it really doing what it's doing, what it's supposed to be doing. So there's such a thing as like connected linear networks that connect one cell to another in a different spot. And, that may come up in East St. Louis if we model the French drain. That might be a connected linear network, which is for things like pipes and conduits and things like that. So is it doing what it should be doing? So we have to kind of go back and revisit a lot of those code selection. We'll talk about Newton-Rasmussen, NWT solvers. You have no idea what it's doing.
I'll drag up here and try to explain what that voodoo is.
Yeah, good luck. I'll just tune it out because I was just voodoo. unstructured grid is another one, and we can give you the examples of that. But so that's kind of where we were stopping for the most part last time.
Yeah, and just to kind of follow up on that, to test these, we have to go and build simple models that we're going to understand. Like when you were doing CLN, to actually, what is this doing again?
What is this doing?
Actually build a simple model and control it, and then, oh, that's what skin factor does.
Right.
That's what that means.
Yeah, it's a lot easier to build a small model you can test and have it run in a few minutes than to try something. Let the big regional model run, it takes 14 hours, and then you realize, oh wait, that's
not doing what I want.
That's not right.
That should be a 4 instead of a 5, or if it's a big model, you don't necessarily see the impact of what you've done.
Right.
Yeah.
So you got to set up your little test case, like with a big hydraulic gradient or a big pumping stress, so you really find out what's going on. And so as we go forward as groundwater flow modelers, new things are going to be thrown at you all the time. Like you go to a conference and you'll say, oh, there'll be a vendor that says, well, I got this model. It's Dutch, so it's great. And it solves the problem by breaking it up into small pieces and stitching them back together. And maybe it is, and maybe it's not. So we need, but it's sort of thing. Well, hey, this has a lot of promise. Maybe one of us should look into this and see if it actually works. Starting with the example problems and then working from there before you go into. So
I think the best example is unstructured grid. That was the first thing I looked at, like my first week here, because that was all the rage at the conference we were at. Then go back and the tutorial example it actually gives nonsense in the tutorial. We sit there and try to run it. Yeah, we can't get anything sensible. But 2 years later, they had resolved all that. So these codes are always under development.
So all of us here have played with these different packages. So I fully expect that 4 or 5 will be experimenting, and maybe with a code to do. There's lots of people have promised the pot of gold at the end of the rainbow with surface water, groundwater modelers. I don't think any of them got really close, but that's maybe something to try out, different packages or contaminant transport. There's lots of things to try out there.
We're using new code, but the contaminant transport code that's accepted MT3D doesn't work with our new flow codes. And so that's why 14th through 24th of October, we're going to do the webinar. We did get that funded.
Yeah.
Where Jim Rumbaugh, who develops Groundwater Vistas, the GUI we used, is going to go through all these new codes. This is East St. Louis. This is critical that we know that our flow model is compatible with a code that works, because we don't want to say, let's use unstructured grid, then find out the solute transport code is garbage with it. We need to find that out earlier.
Yeah, because with unstructured grid, you're kind of doing tricks on the mass balance.
Yeah.
Then you add a contaminant mass balance that you're also trying to do on that, and then you're adding voodoo on top of voodoo, or ghost on top of ghost.
I have a hard time picturing how contaminant transport would work in unstructured grid.
Me too.
I'm really struggling conceptually to wait, how would that happen? If you have grid sizes that are all different sizes, that it just seems like that'd be really hard to do. So I'm very curious about this.
Yeah.
This could be in vertical or horizontal, but if you have flow coming in an unstructured grid, you can make things finer and finer and finer as you go. So it has to divide the flow somehow between these 2 cells based on the relative head in these 3 cells. So it's making a calculation here and making some assumptions, and you know, if this is say 100, and then kind of the regional gradients this way, this might be, you know, 20, and this might be 80 or something. You know, then if you're adding contaminant transport on top of that, where you have so many kilograms or something, should it be 20, 80? So, you know, how's it going to divide that up? Oh, people can see it. All right.
I'm trying to start the webcam up on that little Logitech thing, but it's not reading it just yet. I think it's trying to use that webcam up there. And that's not hooked in, so I just need to tell it to look for the Logitech. It's okay, keep going.
Oh, okay. So the other modeling steps, we'll talk a lot about calibration, yeah, and separate, and that's mostly what the rest of these slides are. Now you froze this again. Oh, there we go. There we go. So we touched on this before, creating the domain of the model.
I just realized that I need to send Janet Agnoletti something this morning.
Oh, well, don't call her. You'll be gone too long. You know, so today we're going to talk about the different layers in the model, or a model, not necessarily the model, and some of what we've done in the past with both the bedrock model and the glacial models. And I'll give you a little background on the Mahomet model. And so we'll talk about the layering, you know, how we went about trying to grid these very uneven layers. And just for review, if this is a typical cross section, we have layers 1 through 4 that might be a sand, layer 2 might be a clay, and some might layer 5, and some of those pinch out. So if you start looking at glacial deposits, there's things that are always pinching out. If you look at bedrock, if you look at a big enough scale, of course, a lot pinch out in central Illinois that appear in deeper units elsewhere. So you have all these pinch outs. Standard MODFLOW requires that if you're going to discretize this and you need this layer in your model over here, that the actual layer has to go throughout the whole model. So you can assign it a property of something else, but the physical layer has to go all the way. So if we have 26 layers in our model, there needs to be 26 layers everywhere. Unless we use one of the new codes that has unstructured grid where you can just get rid of them. We talked about gridding some, nested grids, scaling down. We talked about finite elements a little bit. This is more unstructured grid where you know, zoom in and get finer and finer. And so a lot of these are all kind of the new things that aren't, I want to say, as field proven or as tested as I don't want to say as they should be, but you know, you get the code and it's written and it's put out there, but it's not until a lot of people actually use it and try to make sense of it and actually use examples where the kind of the rubber meets the road and is this really working or is this really what I'm doing? So someone here in this example is trying to, it's a horrible example because that doesn't look like a river network, but it's trying to, you know, maybe add more details right at along the river.
Imagine that being a Ranny well. You know, that's one way that we can zoom in locally and still have it in a regional model.
Right.
So that's one application that I can think of right off the bat for this.
Yeah, that's gonna be tricky.
Or do you want to do the Ranny well with a finite element model?
Yeah.
So a finite element model uses a different geometry And so it's easier to scale down and scale up with triangles than it is with squares. And so, or any shape actually. Well, there's a lot of different options. But finite element is a more sophisticated code that, it's calculating the transfer across each of these triangle faces. It's not, my mouse is not there. It's not trying to do what we're doing here, where you go from one node to two. It's always going from one node to the next, but it's not constrained by a grid geometry. But it's a lot more complicated. Not nearly as many people use it. It's not nearly as user friendly. It's not nearly as understandable as to what's going on. And a lot of the other codes that we would want to use with it are just not there. It's not supported like the grid-based MODFLOW is.
There's a beauty to being able to say, here's my row, here's my column, here's my layer. There you're saying, here's my node. Not the same understandability with it.
Yeah. And then if you want to talk about Voronoi cells, you can talk about Voronoi cells.
I'll let Mike talk about those.
I don't have much to say about them either. From my understanding, a lot of the math behind the triangular element models and the drum element model is very similar.
Yeah.
You're basically building triangles up to drum.
Yeah. So you worked with triangular meshes, is that what you had worked with before?
Oh, okay.
Yeah. And I think you can do unstructured grid with triangular meshes, but I don't know that for a fact.
Visual MODFLOW Flex has the option to do triangular.
They did have triangular? Okay. I'd imagine Vistas does as well then.
I think in the Vistas load up screen they have the Voronoi.
Yeah. Yeah, if you go now and you're creating a brand new model,
It's one of
it gives you the choice to do this or this. When we went from 6 to 7, that's what we paid for.
Yeah.
It's like,
Okay.
well, we didn't even use anything there. That's why I'm disappointed in.
But is it
7,
tested? Does it work?
Hmm?
What did you use the triangular grids for?
Sure what you're asking.
Well, you said, what were you modeling when you used the?
So it was the model that was developed over at Iowa. It's primarily surface water.
Oh, okay.
But it did have subsurface.
Oh, I didn't use a triangular mesh. Well, so this is the rest of that presentation. We'll have a whole separate discussion about river boundaries, but it's just another package that it's added to it, and so you have to make assumptions about the river with the interaction with the aquifer. And so what MODFLOW is doing, this is called a head-dependent flux boundary. So you assign it a head in the river, and it's calculating a head in the aquifer at that cell, and those can be different. So, or they most of the time are different. And so it assumes, or you can put in, some siltation in the stream bed, and then come up with a flux out of that boundary. So if you are a firm believer that your river is a strong groundwater outcrop, like in the Green River lowlands or something, you don't put any resistance in the stream bed. And we'll talk more about that. But that just basically, turns your river cell into a constant head cell of sorts. But where they really come in useful is, for a stream that's receiving discharge, the river is a low point, so that water is going to come out no matter what. And so the playing with the stream bed permeability doesn't do a whole lot. But where we have streams that leak water to the groundwater, it's really important. It's much more important.
Traditionally, all of our models, the stage H riv, that stage in the river, is the same for every stress period. And as we start getting into St. Louis, where we're
Rivers
concerned
too,
about
right?
the
They don't
Mississippi
go up and
River.
down.
What's that?
Rivers don't go up and down.
Yeah, rivers don't go up and down. What? Yeah, yeah, that sounds like a just fine assumption. No,
Yeah.
as we start to get into these contaminant issues and the river going up and down, we can let that vary. If you want to get crazy, you can let the width vary. You can let the permeability vary. If you think at flood stage you get a different permeability.
Yeah. So the MODFLOW model has or the Muhammad model has a constant river elevation into the Sangamon River out here. But what we actually see from the data is that it's only leaking water during floods. And so you can turn on the Champaign Cone Depression or create the Champaign Cone Depression. It goes out to the river, but the river still doesn't lose a significant amount of water. And the field data suggests that it's not losing any water until it floods. So there's a head in the cell. So you can see the water table is drawn on here. Here's the river surface. So you might have an average head in this cell that's maybe a foot higher than the river surface. So you have a gradient of 1 across this low permeable material. Well, it's probably not even 1. It's probably going to be something even much less, a half a foot or something. But then the river jumps up 10 feet in a flood. Suddenly your gradient is jumping, by a factor of 20 or even more. And so you're going from a real small gradient to suddenly, wow, you got this huge gradient. The other thing that goes on is when rivers flood, you get suspension of the bed load. So now what happens to all the silt that's silted in the river during low flow? So there's a lot that goes on there, but we'll spend the whole day talking about the rivers.
You're giving us a lot of credit that we can talk about that in a day.
Yeah, okay. So I just want to throw this picture up here. This is Dan and I, obviously out in Crystal Lake. This is a quarry I was telling you about, the Three Oaks Recreation Area, where it's an old sand and gravel pit. And the pit to the south, it's across a causeway, a wide causeway, but a causeway is 14 foot. It has a water level that's 14 feet lower. It's all very permeable sand and gravel. And you look at it and go, well, there's no way this should hold water, because that permeable sand is just going to drain everything out. And so USGS had a well on the causeway and the water level was 8 feet lower. So they were just using a sand permeability and that 8-foot head loss over 25 feet and saying a huge amount of water was leaving the lake. Well, if that were true, the lake would have been dry. It was so. We didn't really know what was going on in the lake bed, but we assumed that something was wrong and the lake wasn't leaking water like it should have. So I'm standing on a 55-gallon drum that's cut off and pounded into the stream bed, and attached an IV bag to that we put a set amount of water in. So we filled it up with 500 milliliters and stuff. Put it under the water, connected to the drum that's otherwise sealed. And if water is flowing out of the lake, it will leave that drum and be replaced by water from the IV bag. So you can actually measure a flux rate out of, or a volume. Well, you turn it into a flux with the area of the drum, but a flux rate out of the lake. And it was far, far lower than what sand would indicate. We also took a boat out, collected a whole bunch of grab samples of the lake bottom sediment, and it was really fine. There was a lot of plant organic matter that had built up, but we also think that because it was a quarry, they wet mined it, so they're digging up all the sand and gravel with a dredge. The fine material, either gets dispersed there, or when they wash it through their wash plant, gets dumped back into the lake and kind of self-seals the bottom. That's the only explanation I can come up with. But because once you move into the causeway that separates the two lakes, that's native sand and gravel. That's really coarse material and stuff. So, you know, there's no way you can model that 14-foot head difference and put your permeability of sand in there and expect not to have a huge torrent of groundwater going through. So something had to add up, and so that's why we kind of, you know, our model didn't work. So we went out and got more data to try and figure out what's going on. Yeah, so we'll talk about calibration. It'll be a whole nother discussion. You know, how you look at, you know, what you predicted versus what's measured. And I'll just save all these slides for that discussion. But basically, you're iterating through to lower your error. So you're trying to match your either your head data or your contour lines or river fluxes or all those things all together. And basically on the left here, what you're trying to do is you have different measures of calibration, and that's discussed in this book. I think this is out of, oh, this is not out of Mary's book, but you know, you're trying to reduce your mean error is, you know, whether everything's, it tells you kind of whether you're all above or all below your targets, but you could have targets that are positive and targets that are negative. So you have to look at your mean absolute error. And there's some other measure. RMS is kind of a standard deviation sort of thing. And then you can do sensitivity analysis, and that's a whole other discussion. I'm not big on sensitivity analysis for this. This is a calibration curve. This is your calculated versus your observed value. And then plot it up, and if everything's perfect, they should fall on the 1-to-1 line. Here's a bunch of our calibration curves. So you can see I'm very retentive about getting the curves. The Muhammad Aquifer, obviously I spent the most time on that. I can go back and show you what the Northeast Illinois bedrock one used to look like. That's kind of frightens small children, so we won't look at that.
You're talking about the pre-development one?
Yeah. So we'll spend a lot of time talking about that, and Daniel's made some great strides on that and where to go. And then the Kane County one, which we'll talk about that today. You can also map out that error, you know, where it's distributed, you know, where we have the greatest errors, and that tells you where your model may be biased in one direction. You know, quick search in the internet, you can find some calibration curves. This is a horrible one because they got everything on a line, but the line is off. So they're too high at their high values and too low at their low values, which tells me right off that they're way off on their permeabilities. You know, their gradient is way too steep or shallow or whatever that's causing that problem. And our models aren't spot on either. So this is a Northeast Illinois bedrock model. This point was caused by one value that we later found the field books for and decided our value wasn't very good from 2000. But you can see this bias in the west where water levels are way too high. And that's what Devin's been working on a lot. And so he's gotten that down substantially.
Hampton Township. That's right there. It ties into the story on improving calibration there.
Yeah.
These are all, most of these are production wells, and we've gone out and measured a static water level when the well's been turned off, 15 minutes, an hour, 4 hours. These are not exceptional calibration targets like we're dealing with in the Mahomet, where we do have dedicated observation wells. So, you know, having the dedicated observation wells are really nice, but when you're talking 800, 1,200 foot deep wells,
Yeah.
well, we don't have the money to drill those. So we take over some. We have what, 10 maybe now?
Yeah, and what Dan's been doing is putting together a network of observation wells in Northeast Illinois.
Mm-hmm.
So we're trying to improve upon measuring production wells and measuring dedicated wells, but obviously there's not nearly as many of them. And you can see that there's a lot of messy stuff here. That's all Joliet.
Where we have no dedicated observation wells, where we need them the most.
Yeah, you and Nick are going to fix that, right, with prison wells?
Nick is going to help us how he can.
Oh, he can.
But all that to say, this 50 foot, that may not look very good. That's actually really good for the deep sandstone.
Now, if it was a Muhammad, it'd be horrible.
Yeah, Muhammad. Yeah, that would be.
So we'll have a lot of discussion about that. Some time series calibration, we'll talk about that. Because and this was Tom Prickett, whose name has come up a few times, he's a very famous modeler here, did a lot of the early groundwater models. He said a lot of models go wrong with storage, and Northeast Illinois, where you lowered water levels 900 feet, you get a lot of change in storage. But even in the glacial aquifer, storage is very important. So that's why these models have to go back to 1863. They have to go back to the start of pumpage. Because you suddenly can't start modeling in the middle of it, because then you've missed all the changes in storage. I do have a calibration plot on here. I don't even know if I want to explain this. We'll talk about that during calibration. So some of the other things, this is McHenry County, so this is all Daniels. No.
No, I'm not taking credit for this. I'm the last author on this report.
So we can simulate, changes in groundwater discharge, with pumpage, or an increase in pumpage and how that's going to affect discharge. There's a whole lot of pitfalls to this, and we'll discuss those quite a bit, because that's a really important thing that people are interested in. If you start pumping, are you going to dry?
People want to do it, and we've cranked. This is an example of where we cranked results out from our model to look at how much stream flow was impacted. But it's an example where the model was, I would argue, not ready to make that assessment. There are too many issues with this.
Yeah, and this is a steady state model. Well, it has time. It has years.
It has years, but no change ever in river elevations.
Yeah.
There's a whole thing that you do with drain cells, but that's for when we talk about boundaries.
Yeah.
That's what I really think is going awry here.
And then you look at the historical low flow. Crystal Lake is right in the middle of this. Or that's the minus 52 one.
Oh yeah. It's
Crystal Lake. Or the minus 32 one next to it.
But if that's the Fox River hasn't gone down in flow.
The Fox is on the east. Yeah.
Oh, okay, Fox is to the east. Okay.
Yeah. So there's a lot that we need to do on looking at our streams and what impact we're having on our streams, and this is a steady state model, so I'd say it doesn't account for all that. And then none of our flow statistics that we look at are steady state. We look at a statistic. Well, what are we matching to? So this then particle tracking is another module that we can add to that. So this is an example from the Orange Report for one of Montgomery's wells. And then, so I think these are 5 and 25 years. So these are reverse path lines, and it shows you where the zone of contribution to the well is. Now this is interesting because then this well got contaminated by a company that makes all the furniture that you're sitting on. For most of it. Let's see, Flex Steel or not Flex Steel, All Steel. I don't know, big furniture company. But so we looked at, all right, if there was a contaminant plume coming from that plant, what would the concentrations be in Montgomery 13? So we took our existing model, we telescoped it down and made a transport model so IEPA could look at, concentrations of this contaminant that were showing up in Montgomery Public Well number 13. And so that's right along the Fox. So we had to make assumptions about, what the source was, when it got in, how long it's moved, and the mixing, and it came out rather well with our initial assumptions, so we didn't change anything. But you can see the plume is supposed to go under natural conditions, kind of flow into the Fox, but Montgomery 13, we changed the pumping rate on 13, I think is kind of why, but it's drawing that contaminant plume towards it. But yeah, so that's just an example of something that you can add to MODFLOW. And so it also brings up, as we build these models, we're always asked by IEPA to, they have lots of contaminant problems and stuff, and so they want to know where things are going. So as we build these models, we need to keep in mind what purpose we're building them for, but what purpose other people may want them for. And so IEPA used to model everything themselves, but as modeling has gotten more sophisticated, they're relying on us a lot more. And so it's a lot easier for them to come to us and say, well, what's going on here? And for us to do the modeling rather than them creating it from scratch or us sending them our models and then they running the models. So it's, how do I want to say, it's an avenue of revenue. I don't know. I mean, if we could take that task over for IEPA and have it in-house here and get a string of projects from IEPA or a retainer, be on retainer for IEPA to help support our modeling effort by working with them. And so, Rick Cobb, who's charge of public water supplies over there, is a groundwater modeler and has in the past. And we should probably have Rick come over before he retires.
That's a good idea.
And,
Wait, when is that happening?
I don't know.
Okay.
But he's been around longer than I have, so.
Are you going to talk about telescoping models later?
Yeah.
Okay.
I mean, I had a few slides on it, but we'll talk. We can actually pull up that one if we need to. Yeah. So the models. So when you run a contaminant transport model, there's a lot of things that need to work. It takes a long time. You got a whole other set of equations to solve, and so if you're modeling a small plume, because what the contaminant transports take the flow model and do things on top of it. So, there's no reason to run the whole entire flow model again. So you can take a small portion of it, and when you telescope, it sets constant heads or whatever kind of condition around there. And since you're not adding a pumping stress or changing a water level, you're just doing the mass transport, the flow won't change. And so you can get away with doing just a smaller subset. Now, if you want to try to go to transient transport models, then that changes. So if the water level, you wanted to simulate the water level in Montgomery 13, under changing conditions. Whoops, going too far. Maybe. Under changing conditions, then obviously you need a transient flow model and a transient contaminant transporter. You have to run it. And generally people haven't done that because it's very time consuming, but it's, I think, a direction people are moving is try to have more transient contaminant transport models.
We may not have a choice in St. Louis, given
Yeah.
the configuration of everything there. We may have to, but if you go back to the telescoping mesh, one challenge, the idea is you run your big regional model, and then in Groundwater Vistas, our GUI, you can easily extract this, except if you're using unstructured grid, which it doesn't pass boundary conditions.
Oh, they're all zeros, yeah.
Yeah, which is an issue, a big issue. Jim's explanation was, just build a nested grid, but like you said, you're carrying all kinds of extra computational energy there, but you have to have boundary conditions here. And if it's transient model and you have a well here that's changing, these need to be updated transiently from. So you have to be careful here with the boundary conditions in this case. But it may be an option, it may be something we have to do in East St. Louis, but it's something to be careful of. If these new packages don't work, or if they're just too slow, it's too computationally. Here's your quad tree refinement, and now you're trying to run contaminant transport through a quad tree refinement. What is that computationally? Yeah, that I don't know. So
I don't know.
But those are I think this will be really important in terms of deciding. This is how we've done it in the past.
Right.
And it's worked well. But how do you update that? How do you make it transient?
Right.
Yeah. There's not going to be one silver bullet for everything.
Yeah. No. And there's going to be a lot of experimentation on this stuff that we're going to have to do in the early going. I think.
Yeah. No, I think so. Yeah, maybe someone should be reading up on transient contaminant models.
I like how you looked around the room. You didn't look at anybody in particular. Normally,
You're too busy, and I'm not going to do it.
You gotta find things to keep you busy when you're tired, man.
Yeah,
That's a good.
I do, I guess.
Some good busy work. Why don't you just write one for us?
All right, that's
ooh,
fine.
you use Crunch. Crunch flow.
In a few classes, not as part of my research.
Yeah. No, we've thought about all these different options. I don't think Crunch is necessary for anything we're doing here. I don't think, but
Well, and we're not getting into contaminant transport until
year two.
two, so we have.
It's just a matter of making sure that the model that we build.
Right.
I'm
Yeah,
worried.
yeah,
It would be
yeah.
very easy to say, wow, look at this great flow model we have. That was so easy to do with unstructured grid. Oh, I can't do anything I want in terms of the plume now. Yeah. That's my biggest concern. Or for some of the needs that you're going to have for the model long term.
Yeah, because that's the other thing we need to think about is, setting it up so that we can use it to establish like a efficiency protocol for the whole system.
Yeah.
Eventually, I don't know how hard it would be, but like just install floats in the wells so that they turn off and on based on water levels on their own. So you don't have to. Yeah, because I've talked to Daniel about this, but like essentially my long-term goal with the whole dewatering project is, I don't know about showing you any of the hydrographs, but I mean it's just peak and valley, and it's just because of the manual switching on and off pumps. So if we could get it to where we could keep a pretty even hydrograph where we just have a target elevation in each area and try to just keep it there rather than, oh shit, it's above it, turn the pumps on. Okay, it's below it, turn them off. So that's something to keep in mind.
And you're thinking the way to do that is with the float system you're describing is kind of a physical setup.
Yeah, I would think once we
some sort of telemetry-based setup.
I think it would be a little bit better as far as maintenance goes. That if you put a float in, then if something goes wrong, Pete can yank that pump and figure out what's wrong with the float.
Fair.
Whereas if it's all telemetry and stuff, he's not gonna have any clue how to troubleshoot that, and so it's gonna be expensive because he's gonna have somebody.
Sure, and the physical setup should be less expensive anyway, long term, like or initially.
Right.
It should be less expensive.
Yeah.
Okay.
But if you could establish, we already have our margins established, and you just set the float up for,
between here and here.
Yeah. But there's a lot of wells down there.
Oh, EICMT, that doesn't sound good.
Oh, phase one. This is, I don't even know if you've seen this.
Probably not.
The phase one report.
Oh, yes, I did see it.
Yeah. Need a copy of it.
Okay, so let's switch gears a little bit and talk about the geology in a model. So obviously the geology is going to be all the layers and the elevations, and with the bedrock, it's fairly easy. So we've had bedrock models in the past, and we've had glacial models in the past, and the two really haven't intermingled too much until more recently. The bedrock, it's a lot easier from a stratigraphic standpoint because it maps on the statewide, it's deposited in the Cambrian, Ordovician, whatever, large units. They do change a little bit with location. They change quite a bit in Wisconsin. And so the bedrock, and it also goes way beyond Illinois, which is another problem. So, how we divide up the bedrock into a model has been different. The original models of Chicago just called it one aquifer and modeled it as a two-dimensional system of the deep sandstones and intervening units. And they were not far off because they basically had the transmissivity right. And so we've gotten much more sophisticated then in adding up all these different layers in with all the complexity. But if you add up the total transmissivity, it's still fairly close to what Tom Prickett had in the 60s. And so it still works fairly well, although now we have the faults and the multi-aquifer wells and all the other things going on. But, if you add all that up, it's still fairly close to what the 2D model originally had somewhere. Yeah. It's not.
Well, and back then, most of the wells were multi-aquifer wells, which basically meant the two sandstones that were being modeled, the St. Peter and Ironton-Dellsville, all this material between that may have been an aquitard, wasn't, because there were just too many holes poked through it. That's actually changed, where more wells are now going here, and that's been a major shift in what we model. But in terms of the geology, you could easily say transmissivity of that plus transmissivity of that, same head. Up until 2014, we always treated them as the same head. So yeah, it worked fairly well.
Let's see. I don't remember what I put in. No, that's not what I wanted.
But we try to go through and like the Pennsylvania, Mississippi, and that's too many stratigraphic units to list in this table. And so we create what we call hydrostratigraphic units just to lump all these like units together.
Let me get another PowerPoint real quick.
That can actually go a bit awry from time to time, like the Maquoketa, we call that a shell. But there are some communities that use a limestone unit that's very thin within the Maquoketa. The Fort Atkinson, it's just so local that we don't really worry about it in the model. But for those communities, our model's not going to be able to do anything for them. And there's some things we can tweak, but yeah, we try to lump as much as we can into like. And then sometimes it's not the geology, but sometimes like here where the Mount Simon is fresh water versus saline, we put in a different hydraulic conductivity for that just to account for the density difference, the salinity. And so we have the Mount Simon divided up into 2 layers. We really don't have to do that. We could just have 1 layer, but you know, but based on the geology. Right. But here it's let's go ahead and do that a little different.
Are there any wells down in this Mount Simon?
Yeah.
Do you have any mixture?
Yeah. So have you seen the Aurora well? You've not seen that video. Okay. You actually see Mount Simon water coming up. It does not look like a groundwater well. It looks very much like just water bubbling up from the deep. There looks like there's a sharp gradient between the two because it's not really mixing. It's just there's definitely an interface there, whether that's density or something else. It's hard to say. I'll show you that video, but we definitely have some old wells, and they're bringing up saline water into the freshwater aquifer.
Right, that's what I was curious about.
Yeah, and so we get that more in Cook and DuPage. In Joliet, they did drill a well into the Mount Simon. It was a flowing artesian well. This was back in the 30s. There were salt crystals that formed all around the base just because of the high salinity of this well.
And where's the salinity coming from? You have any idea?
I mean, it's just.
I'll show you.
That's a good question. Yeah.
I've never heard of that.
Yeah, just the deep system just has that natural salinity.
The interior of a plate.
And so that's kind of where we go a little bit off the geology then when we define.
Right. Okay.
Yeah,
I think I need to back up just a little bit and explain a little bit of background on bedrock in Illinois for those of you who are not from Illinois. And so, you know, if you're not a geologist, I always have to explain time periods. But, you know, way back from the beginning, but then, you know, 500 million years ago, if this is spiraling up till now, we had the Cambrian and Ordovician and some Thorian, Devonian. So all our rocks are old, very old rocks. Then we had some in the Mississippian and Pennsylvanian. We largely ignore except as a confining layer, and then everything else is right here. You know, so we missed all the dinosaurs and all the little horses and everything else.
It's the glaciation that
scraped it away. So, you know, this is what Illinois used to look like. So you go to Chicago, you go to the quarries, and you can find brachiopods and trilobites and all that kind of good stuff, you know. Then we have the Pennsylvanian, and nothing against Pennsylvania. Well, not too much. in the Mississippi and just mucked everything up. So that was the advent of land plants. And so land plants generated a lot more weathering with their roots and created a lot more silt. And so the sand and then covered over what would have been sand dunes in previous times. So the sand got a lot more dirty with time. So our original Mount Simon, St. Peter, and Ironton Galesville make better sandstone aquifers because they don't have as much crud in them because of the damn land plant. It screwed everything up.
You have a scale for that dragonfly there?
No, I bet it's huge though. I have to ask Marshak.
Yeah, some of them are like 5-6 feet long.
You know, of course, then we had the ice sheets come. Illinois is right in the middle. Of course, it went all the way.
That's the
It doesn't-
early one, right? Because you had another coast that went farther south.
Yeah, we covered almost all of Illinois. So Illinois is kind of unique with Michigan and Iowa and Indiana and half of Ohio that we deal with glacial deposits. And so, you know, and that's one of the reasons why our surveys tend to be bigger than some of the other surveys. It's because glacial deposits are a lot harder to deal with and a lot more complicated, you know, than the geology in, say, Alabama or whatever. So a little bit about our bedrock. In northern Illinois, obviously, it's freshwater. You can see the freshwater saline kind of line there. And so the bedrock, our bedrock units go all the way into Kentucky. But we basically cut off our models to where it's freshwater. So even the St. Peter sandstone, for example, as you go to Decatur and south, is full of brine. So for our freshwater model, since we're interested in water supply, we don't really care about the bedrock in southern Illinois. The Mount Simon, of course, gets to be 10 or 14,000 feet now, you know, and it's so saline, we don't need to worry about it. So so I guess I'm one of the few here who's dealt with southern Illinois a lot, but it has a whole other list of, like, you're the only one, issues. So it's brine. And so it's largely been the purview of the Geologic Survey to deal with the deep bedrock. But I've gotten involved in quite a few things where there's been problems at the surface because of what's going on. So saline water, we have a lot of oil production. Fracking is kind of a big thing. We had a whole committee and legislation on fracking. I think we have someone from the state with a lot of fracking that could take that over. Pennsylvania joke.
Oh, yeah.
Texas joke.
You're just vertical. They do horizontal fracking in Texas. I guess they do all over the Permian. Yeah, of course. All right. Well, good. It's got 2 volunteers. Waste injection. That's not only like oil field brine. So when you produce oil, you produce a lot of water with it. That gets injected back. But we also have hazardous waste injection into the Mount Simon because it was cheaper than treating it. Carbon sequestration, which is where you're dumping carbon down into the Mount Simon to keep it out of the atmosphere. That's what keeps a lot of people busy at the GS. And we have a lot of natural gas storage domes. So we get gas from Pennsylvania or Texas, gassy people, and then we store it. We buy it in the summertime when it's cheaper, store it underground, and then get it. So there's the Manla field just north of Mahomet that had a leak a while back, which has kept me busy. But so in the summertime, they're putting natural gas in, and in the wintertime, they ship it up to Chicago.
What sort of formation is it?
It's in the Mount Simon sandstone. They tried it in the St. Peter first, but it leaked out.
really, even right, the ones you were showing me right around here, that's
Yeah.
Mount Simon?
Yeah, this is Mount Simon. So those are all 4,000 foot wells.
Wow.
Then you go up to Bloomington. I don't have a map of them, but there's the ones here, and then there's a whole bunch along the south anticline on up into LaSalle County, McLean County. I think there's 14 or 15 of them where they store the gas. Yeah, and then there are some freshwater bedrock aquifers in southeastern Illinois. Just south of Metro East, of course, there's the karstic limestone down there.
So our water supply planning model cuts off roughly there.
Yeah.
But there are these other issues. Should we be looking at expanding our current model domain to address some of these?
Well, if we did that, then we'd have to use CWAT or a model that takes in the density into account.
Which unstructured grid now does. That's actually one of the things we're going to talk about. Jim's going to talk about in October.
Yeah. Well, if you want to model Aurora 18.
Yeah.
You do.
That's the second time that's come up. We're going to have to show that video.
Yeah.
Your water supply model, regional model extend all the way to the Mississippi?
But not to Metro East.
Not, but it doesn't. Yeah, it doesn't go down to.
It like cuts
All
off.
right. So.
Yeah, it basically cuts off at that line, from what I recall. Maybe
East
a little above.
or west of the Mississippi is currently inactive, but that needs
West of
to
the
change.
Mississippi is currently inactive. We basically treated the Mississippi River as a flow boundary, but
it only
there's-
works for the first
there's
2 layers.
shell
Yeah.
and carbonate underneath the Mississippi before we get to the sandstone, and so we found out no, it's not.
Yeah, there's that.
And yeah, I think Iowa has. How does it go? Iowa has water flowing into Illinois. And
Yeah.
we have water
Nothing.
flowing into Iowa based on our modeling. So we are working with Iowa to get some data. Devin's doing a lot of that to try to improve that simulation. But
Yeah. So this is a general
Yeah,
outcrop down the center of the state. So you can see this is the Illinois basin where all these rocks get a lot thicker and deeper. And then up in north, that's not shown here, but the sandstones a lot of them come to the surface either in Illinois or in Wisconsin. So that kind of serves as a recharge area. And so there's limestones and shales and other things. So that's why there's fresh water up here. There's some discussion on whether when glaciers came, because the glaciers were a mile high, there's a tremendous amount of head underneath them, and it forced a lot of fresh water in there. Are we just taking that fresh water back out?
And therefore it's not really being recharged with the.
Right, we're just taking the fresh water out. And then for most of southern Illinois, the Pennsylvanian and the Mississippian are at the surface, and they're largely shales. So once you get south in the state, the bedrock's not really even considered, other than domestic wells. But there's a few oddball, rare bedrock wells in the southern part of the state that are in the sandstone. And some of the oil is all in some of the sandstones that are higher up in the system. So there's a basic difference in these units. They all exist all throughout the state, but they're a lot deeper.
What's the Solarian? The black one? Why is it black?
Yeah, that's I think the New Albany Shale, isn't it? Is what they're showing there.
Yeah.
It doesn't say in the caption.
Doesn't say in the caption.
But
that's also
It
hasn't.
says,
that's
it
just
has-
age.
It has the
So
age, but it doesn't.
yeah.
It just says layers of sedimentary rocks at various
Yeah.
stages. It doesn't give you what it is.
Yeah. Okay.
I'm just curious.
Well, we'll get to that in
Yeah.
a bit.
This is a good graphic for
But then
Rockford,
again,
though, 'cause you can really see. the sandstone in relation, like
What happened in the
Rockford doesn't
Solarian?
have
dude?
supply
Yeah.
No, I'm trying to remember the age and the
instance of what
different ages
the
of
surface
the
has
Yeah.
contamination
St. Peter's and whatnot.
risk.
But
So-
there's-
So this is the bedrock geology. So all these greens are all the Pennsylvanian, and the blues are the Mississippian. And again, these are mostly shales. There's some coal and some small sandstones. The Carbondale Formation appears, and it's got quite a bit of sandstone in there. But in northern Illinois, the Pennsylvania Mississippian has been eroded away. We know it is there because it appears in displays at the whatever that displays disturbance is, whether it's a meteor impact or not. There's actually Mississippian rock. So this is all the Silurian. We think in Chicago there's actually a lot of Devonian shale before the glaciers came, and that's probably because there's little remnants found here and there. For the glaciers, when they made the Great Lakes, basically they carved out all the Devonian shale out of what's now the Great Lakes, and that's why the Great Lakes are where they're at, because that was all the really weak rock, and that's what made all the till in the rest of the state is Devonian shale. That's kind of a simplification, but Champaign is right here. And the LaSalle anticline kind of goes through here. The Sandwich Fault goes through here. The Plum Creek Fault goes there. So, basically where this green stuff is pretty much an impermeable cap on all the rest of the bedrock system. So, we can get recharge to the Silurian system in Champaign County, for example, where it's underneath the Muhammad Aquifer. But so basically, whether it's purple or where the Silurian, Ordovician, and Cambrian units are, that's where there's fresh water in the bedrock system. So this is a better stratigraphic column if you're a geologist than what was in the report, but this is kind of the important units that I like to point out. So if you're not familiar with the geologic column, these are older rocks getting younger as we go up. So the ages are in here. No, ages aren't in here.
That's
Thickness, yeah.
ages
So
are the next column over.
at the very bottom, we have the Precambrian bedrock. It's not exactly an OFLO boundary. According to some of the isotope people, they think a lot of water is actually coming up from the Precambrian.
Yeah, that's cool.
So I don't really know what we want to do about that.
Who was that again?
Sam.
Oh.
Uh,
Talk about.
yeah, he does.
Yeah.
There's about 5 people at the GS that know what they're talking about.
Yeah.
We'll heard of Sam. He's one of them.
Yeah, you heard Sam. It's like, okay, yeah, I'll buy what Sam says.
Yeah. And then we have the Mount Simon, the Ironton, Galesville, and the St. Peter, which all are the important aquifers up in Chicago. The St. Peter is not it's on an unconformity, so it varies in thickness quite a bit, even on a fairly small scale. Then Maquoketa Shale is a major confining unit in the Chicago area. The Silurian Dolomite is another important unit. That's a major aquifer in some of the suburb area and in northwestern Illinois. Then there's other units in here you'll hear us talk about, the Galena Flat, the Dolomite, and the Perry Chain, and all those other kind of stuff. Those are secondary. Well, I don't want to say they're secondary. They're important, but these are kind of the main units that we talk about.
Just don't let Devin hear you say it. You're
Quite
okay.
a bit. The New Albany Shale isn't present in northern Illinois, but it is in southern, and that's the source bed for the oil. The oil is found much higher up in the system, and those names change a lot because those sand layers aren't continuous. They're much more hit or miss. There's a lot of channel deposits and other things in the Pennsylvania. And if you're around the U of I geology department, you've heard of cyclothems, or at least read the plaque outside the Natural History Building. Those are all up in here where you get this fluctuation in sea level that caused this whole variation in sand, silt, coal, and limestone to all be formed in the sequence. The sea level changes back in the older times were much more long term, and then they got much more periodic in the Mississippi and Pennsylvania. But and then the Heron coal is the main coal deposit. And that's what is one of the primary coal deposits. It's the thickest around the state, and if you look at where the coal mines are, it's often revolved around the Heron coal, although there are some others. And then there's some units that only appear in the very toe of southern Illinois. Don't need to worry about those, but then the glacial deposits are a whole thing unto themselves. So speaking of Sam, these are some pictures he took up near Galena, of the Galena Platteville, and this was in 2012, I think. This is an alfalfa field. Alfalfa has really deep roots, and so the alfalfa was finding water where there were fractures in the limestone. So that's, you can see the corn in the background of that field. Yeah. So it's not quite a grid structure of fractures, but you can see, yeah, there's quite a few different things going on. There might be one or two red herrings in there that are ditches or other things, but yeah, but that's a really good picture of that. Well, here's the short version of Northeast Illinois. We have these sandstones dipping to the east, recharge area in the west. And we'll skip over all this for right now. Yeah, that's pretty much Sandwich Fault Zone. You'll hear a lot of discussion about that. That cuts across northern Illinois. That we have different units at the surface in Kendall County on that.
Can you go back? We're just talking about this. This one.
This one?
No, the next one. So the magic line that they chose and said, oh, we're going to drill a well just south of the magic line, when the reality is it's a bunch of up and down ground blocks. And so when they're doing that, they're just they're putting it in a very disadvantageous place. And so one of the things that we're going to have to do with Joliet is convince them, well, 31, they want to put it right there. We need to make sure that they understand that's not a very advantageous place. Allison understands it.
Flint Hills understands it.
Flint Hills understands it, and I think Allison understands what's going on at Flint Hills. So I think it'll be a pretty easy sell, but that's where some seismic work can come in and maybe help with the distinction. But yeah, this is a great question marks. Really, I think there's not much question.
Water levels are drastically different on either side.
Yeah.
But, well, for the question marks are there for geologists who want the exact line, whereas for water supply planning,
This should be
there
caution,
are no
caution, caution.
Yeah, there are no question marks. There's a big caution tape.
Yeah.
Yeah. So the units, this is an old slide. Dan has made much better ones, but the units are cut off. So you can't have flow. So when you model this, you have a layer for the Ironton Galesville, right? And you have a layer for the St. Peter. But if you have a fault and your model layer, say this is model layer 5, and then this is model layer 5, this is the geometry that you put into, but the model doesn't know that. So the model can have flow going out this space and coming in this space. So the flow budget is dependent on the model layers, not necessarily the geometry. And so you think, oh, if something is pinching out or something is offset, I won't have it. The model will automatically assume that there's no flow. That's not what MODFLOW does. So
does that mean you need to adjust your layer structure on both sides? Does that mean like once you hit the sandwich fault zone, layer 5 on one side is the end cell, but on the opposite side of that, you model it as the Galena Flatville?
or layer 7, you can do that.
Is that how you would address that?
You can do that, but it gets difficult as the offset becomes less and less, and then
Yeah.
you know, if we come in or out of the board, then at some point the Ironton Galesville becomes one layer again.
Right.
It also makes it hard to graphically show, well, what's the water level in the St. Peter? Then you can't just pull up layer 5.
One layer, yeah.
And so, and we'll talk about that, but yeah, a lot of what you want to do is built around seeing your results. So if I have some results in one layer and some results in another layer, it's going to be impossible to look at.
Okay.
You know, then you're just kind of looking at, well, you got to look at this slide to see what's going on north. You got to look at this slide to see what's going on south.
So then how do you end up at?
So you have to put in, well, we wound up putting in is a low
just
K.
like a zone of,
Yeah.
throughout every single layer.
Yeah.
Yeah, we should have Dan give his thoughts for data MODFLOW, where he had a lot of good data from the 40s, this very big pump test that he ran. Have you seen that yet?
I think I saw when you gave your presentation, your brown bag or your.
Oh, yeah.
Didn't you throw some of that?
I think I had like 1 or 2 slides from it.
Yeah.
But the full extent of it is pretty interesting in terms of what is that K value that we assign. He was actually able to get some more accuracy on that than we've had before. But and the way he's done it is, well, he could talk about specifically the way he did it. But it's what George said. You assign a lower K. Unstructured grid does have an option that lets you toggle on that accounts for geometry of layers, and that's all I can tell you. I don't know what kind of voodoo it does and if it would try to restrict flow here or not. I would be very concerned with trying that, but that may be something to look into. I've never tried toggling that one on.
Yeah. So with the finite difference model, we have our layers doing all these sorts of different things based on the geology. But the flow is calculating is always above and below and within the layer. So, you know, I'll show you some more examples in glacial aquifers where you get what looks like all these little isolated sands because the layer is steeply dipping, but in reality it's calculating mass balance. You know, even though they look completely offset, and you know the elevations are completely offset. So I guess what I'm trying to say is MODFLOW doesn't recognize those elevations.
Right. Yeah, and I guess that's what I'm trying to understand is that when you can replicate the offset with the elevations, and then in order to replicate, you have to go a step further and replicate the change in conductivity between those two.
You have to replicate the effective resistance here.
Right.
And the interesting thing is it's not no flow, like it may look here. There is flow that goes from here to here.
Yeah.
Vertically.
It's just orders of magnitude less than what we're dealing with, at least in the horizontal direction. In the vertical direction, Devin said that there's some different things that could go on, but.
Yeah, but that vertical direction we're almost then making horizontal here. What's effectively going here down over, because this is flow basically going here into here, we have to put that vertical within that, and that's where that resistance is really coming in. What is the vertical resistance? We're assigning that horizontally.
Okay,
that kind of makes sense.
Yeah, I think I was talking about something different. I was talking about more about the physical relationship of faults in the literature, but that's fine. I get what you're saying.
So this is the geology that you put in. This is the geology we see on the screen. This is what MODFLOW sees.
Right.
And so what it sees is these different layers, but because this is varying, so our transmissivity here might be 5, it might be 100 here, and if this is where our cells are, it might go back to 5, then up to 20. So what it's going to see here is a 5, 100, a 5, and a 20.
Yeah. Okay.
So it's in each of these cells, it's calculating transmissivity here and using that. So this elevation, if it's, say 600, 610, and you have a 580 in here, whatever, say 680, sorry. Those numbers don't even enter the calculation of the owner. It looks, it'll use it to figure out what the transmissivity is.
Yeah, but then
Make
you
a
have
K
that
value.
Yeah, you can
Yeah,
simplify the grid.
Elevation isn't in Darcy's law anymore.
Right. No, that's right.
So if you can have a steeply, well, let's do that up very long. So if I had a steeply layer coming through like this, and so what my model layers will wind up looking like, if I can draw a curve over here, is it'll draw that unit something like this. So what you see, I should make it go all the way up. So if your model grids are, vertically like this, it sees this as one unit, just like it's over here.
Yeah.
Even though our grids
Or all
don't match.
Right.
So when flow leaves here, it's going to come in down here. Even though this is all, say this is all a big hunk of till, and this is sand, and this is till, then this flow goes into here, this flow goes there. So they're disconnected in your thing.
Yeah, okay. I get how that's useful in most situations, but then when you actually have an offset, a true offset, it's not doing what you want it to be doing. So you have to go a step further.
Yeah.
To replicate what's actually going on. Yeah. Separation.
Some other just groundwater things in Illinois. You've heard of galena, the mineral, lead. Or in southern Illinois, you have fluorite. So those are all what they call Mississippi Valley type deposits, or caused by redox changes in aquifers and the flow of groundwater over very long flow paths. So southern Illinois, there used to be a mountain range in southern Illinois in the past, and so it drove groundwater flow up to the north. And then when it hit different conditions in the Galena Platte, where there's oxygen or whatever, that lead deposited out. And so that's where you get these ore deposits in different areas of the Illinois basin based on that. Likewise, the oil in Illinois also migrated long ways in groundwater. So this orange is where the New Albany shale got cooked enough to form oil. It's the only place where it was deep enough and hot enough to make oil. And so, but oil is found in this black area, way even up here. And that was all the oil moving into the sandstones above the New Albany shale and migrating with the groundwater flow that was going from these mountains in the south up towards the north. So our oil pattern, where we find oil now, are all in groundwater traps, not, and there's not in the source bed. So you would never have any large-scale fracking in this area because it's already in the aquifer. That's how it got there in the first place. So you could do tertiary recovery and stuff. If you're going to frack, you're going to frack in these original source beds.
Right down near the Magic Ball, huh?
Yeah, grease it up, let it flip. So this is a Heron coal, and this is where a lot of this is where the underground mines are and surface mines. You get this outcrop out in Danville, and you get some up in north. So if you go north up to Rockford, you'll see spoil piles. Over south of Danville, you'll see spoil piles, but most of it's in southern Illinois. So we don't do a whole lot with coal. There's some acid mine drainage and those typical sort of problems. We don't have it as bad as Pennsylvania. No one has it that bad. Does everybody know how fracking works? You pressurize a unit and to the point where it cracks, and then the fine sand gets in the cracks and holds them open. So where does all the fine sand come from? St. Peter sandstone. So we've largely just dealt with it with new mines going in near Starved Rock State Park, and farther north in Wisconsin, there's a lot of frac sand mines that open up because that is very fine, predictable sand, and it's the right chemistry and whatever, that it's great for frac sand. I mentioned deep waste injection a little bit in Illinois. So Hennepin Steel, for example, discharged something into the Mount Simon. I forget what they did. And there's some chemical companies over in Danville. There's different classes, and I won't go into that, but you can, the Illinois Basin is heavy enough brine that you can discharge waste into it without worrying about contaminating it. Then there's enhanced recovery where you're injecting something to try and flush the oil out.
Are they really injecting treated wastewater?
I don't think any of that's going on in Illinois. It's been discussed.
Southwest states.
In Illinois, if it's an aquifer, a drinking water aquifer, it has to be treated to drinking water standards.
Then why would you even bother with it?
Yeah.
Aesthetics.
Yes.
Purely aesthetics. In a lot of places, people want to believe, people don't want to believe they're drinking out of their toilet. And so it just putting it in the ground and then pipe, in El Paso they do that.
Right.
They pump it in they put it in the ground, pump it to the other side of the mountain, pull it out.
Oh, look, it's all fresh.
Yeah, I mean, it's exactly the same water, but they get to tell the PR story of, oh, we send it through the pathways that have been used for millions of years.
Yeah.
It's pure aesthetics.
So with all the oil fields in southern Illinois, there's always brine disposal wells that go with them. So there's usually about, I don't know, one brine disposal well for every 5 oil wells. If not, it gets dumped on the ground, and you get burns and nothing grows there for a long time. So this is a well over in Danville. And this is a salinity profile. So these are permitted injection wells. And down in Tuscola, south of here, there's a bunch. Over in Danville, there's some. So these aren't the oil brine ones. These are ones used for other waste. But I put the salinity on here just to give you an idea where the fresh water is. And then this is a St. Peter down here, I think. Yeah, SP. Over in Danville, if you tried to use the St. Peter, it would be, 15,000 parts per million of salinity. So that's halfway to seawater.
Yeah.
And so by the time you get down to the Ironton, Galesville, Emmons, Potosi, you're at seawater. Then you get down into the Mount Simon, and it's yeah. So why is it more dense than seawater? Nobody really knows why it's so dense down there. There is some influence of the Precambrian of stuff coming up. Is it seawater that's left?
Yeah, where do they come from?
Yeah.
Or maybe they were like evaporated salt deposits that were in layer that later was put back into solution.
Yeah, maybe, I don't know. But so that's why we're not modeling it.
Yeah.
A is extremely dense, and so all your groundwater flow equations go out the window
Right.
if you're using just fresh water. So, and that's one of the reasons we don't want to extend our model to the south. But what kind of boundary condition is that?
Right. Yeah, that's weird.
I mean, there's not a whole lot of gradient, so maybe a no flow isn't that far off of a boundary condition. I don't know. You know, compared to what we see in freshwater. But if you're trying to run a model out for, you know, a million years to do ore deposit stuff, then yeah, then you need a different model.
I'm curious how well SORAB's modification of the code to include density,
Would work with
for say,
207,000. Probably
or
not.
just how well it works in general. But yeah,
Well, I mean, what do they use when they're trying to model like saltwater intrusion along coastlines and stuff like that?
CWAT or unstructured grid is being used more frequently. But
Yeah.
or an analytics solution, I've seen that too.
So these are some of the possibilities of where you could trap CO2. So you can see Illinois is one of, I think, the major player as far as, well, they have it labeled as the St. Peter or the Mount Simon, I guess both. But these are in storage capacity in gigatons, I think. And Illinois, they're at 23, the Michigan Basin's at 10, and the rest of them are all significant. Or the Morrison Formation in New Mexico is at 18.
So the blue, those are existing.
No, those are potential areas.
Oh.
You know, so we have some spots in the Midwest and some spots out. Yeah. So, you know, our experience with storing natural gas in these formations is very relevant to how we're able to store CO2. Yeah, so again, this is a depth to the top of the Mount Simon. So up in Joliet here, we're less than 2,000 feet-ish. And it gets shallower as you go up into Wisconsin, obviously, where outcrops. You know, we're at 14,000 feet in Southern Illinois. You know, so yes, it's the same rock, but it's quite a bit different. Thickness also, it gets much thinner in Southern Illinois. So the source of the sand was up to the north somewhere, so it's much thicker. So if you're gonna do capture, you know, you got to have a fairly good thickness of sand. And it has to be permeable, so that's kind of why Decatur is kind of in the sweet spot as far as injecting CO2, but we're not going to have CO2 injection in northern Illinois because it's too shallow. Well, I shouldn't say that. It might happen. Carbon sequestration, yeah, we're just pumping the CO2 down. It adds an extra 20% of the energy to the whole process. So because you're fighting 5,000 to 6,000 feet and the head down there, you have to displace that brine that's under enormous pressure. So I think the injection pressures are on the order of 4,000 psi. You know, so you have to create all that energy in order to compress your CO2 enough to get it to flow into the formation. So
And then and then they just cap what do they do to hold it in there?
well, hopefully it just forms this big bubble and stays down there.
And does that, it's not really that relevant.
But
As far as like putting that much CO2 down there, you get.
well, what happens is, according to the model that Peter Berger did over at the ISWS, it's acid, right? So you're dissolving calcite, but as you get farther away, it reprecipitates. And so you're creating permeability near the well, but then you're creating this donut of secondary cementation farther away. So it's a lot more complicated than just putting an inert gas into an aquifer. And this is a man-loved gas storage field north of Mahomet, where we had a leak not too long ago.
Did you name that?
No, I did not. It was actually Mr. Manlove was in charge of people's gas
Sounds
for
like
many
it's
years.
something South Park.
Kind of like Mark's email address.
I never did call him man liquor. That's good.
We had a guy named Mark Amlicker.
Oh my.
And so his email was
M.
M liquor.
Oh,
So
God.
it was just man.
We did have a Chinese employee over in Peoria, and I won't even say his name because it's too embarrassing to say what his name is. And so this is a dome in the bedrock. It's called a dome, but now we think, or Steve Marshak, the geology professor at ULI, thinks that this western is really a set of faults, and that we've been calling it an anticline and a dome, but he's been revisiting all that.
Where is this in the state?
So Champaign is right down here. Muhammad, this is a township. So these are all square miles. So this is the perimeter of where gas can go without escaping somewhere else. So there's a natural, or there's a dome structure in there that is holding the gas. And you can see all the wells that have gone in there. So it was in 2015, 2016, one of those wells failed. And that's where the gas came up and got into the Muhammad.
All right, I read about that.
Yeah. So that was a long sidebar, sorry, to kind of give you some idea of the bedrock in Illinois. And then, so when we talk about the layering, go back to your report here, if I can. Oh, I have to open it again. Yeah, Windows 8. So in the model, oh, that's in here. Okay. Oh. Can we get Windows 10 on here?
As soon as I can get people to clean old model stuff up. Actually, we're getting a server to put our model runs on. As soon as then we can clean off Modus and just basically start from scratch with it with Windows 10.
So we have our ages that we refer to, fluorine, dolomite, or whatever. And then we have our stratigraphic names. We'll have to have a whole separate lecture on the glacial geology, but and this is how it's sort of been generalized or boiled down into the model in what is called a hydrostratigraphic unit. So we have the Eau Claire formation, and actually made up of different members. One sandstone member, which we've lumped in with the Mount Simon. So, because the geologists like to break everything up into different units and stratigraphy. So technically the Elmhurst is part of a different formation, but since it's sandstone, it's very similar to the Mount Simon, it's lumped in with the Mount Simon. And then the other two members, the shales and the carbonates, are put together in the Eau Claire. The Ironton Galesville are two different sandstones that are right on top of each other, so that's lumped into one. The Eminence, Potosi, Franconia, in past models, that's all been lumped into one. Now, kind of divided it into two. And that can be helpful, like in Western Illinois, where one of them sort of becomes an aquifer. And so that may be more true for the Galena Platteville. They're both dolomites, but they act a little differently. One's more susceptible to weathering than the other. So, right now it's one layer in the model, but it may become two. But it's one hydrostratigraphic unit for now. But there'd be other reasons for dividing some of these units up for modeling reasons. And so, if we have, say, a large cone of depression in Joliet, wasn't flat. So there may be a modeling reason to break some of these units up. If we have, our land surface up here, our glacial stuff, and then say we have a thick limestone layer here, and then a sandstone down here, or this may be Hampton Township or something. So if you have this as one thick, 400-foot layer, and you have a 200-foot layer here, and say your head starts to fall in there, well, then you got to be more concerned about, units going dry, or if you go down here, does this all dry out? Does it really dry out? So there may be advantages to, dividing this up into multiple layers, so you can see visually, well, there's a lot of desaturation going on, because otherwise, if it's only one layer, you wouldn't see it till the whole thing goes dry. The storage values may be different. If it's all confined, it's all specific storage and doesn't matter. But if you have specific yield where water's actually draining out and you want different thought experiments, maybe it's better to divide the unit up. Some of the solvers might be happier if the unit is divided up and some was allowed to go dry, but then, we know if there's flow in here, you don't want flow going into a dry cell because it doesn't work. So there may be all sorts of advantages to dividing a layer up, especially if it's kind of at a zone where things are actually desaturating or things like that. If it's down deeper in the system, it might not matter. Or in Hampton Township, for example, you may find that you have a lot of wells that just go into the top of the unit. And if you go on a field trip to Wisconsin and you look at the Galena Platte and you go, oh, I'm looking at this giant road cut and there's all sorts of springs that are appearing. So if you go to the Highway 161, has a brand new road cut in it. So the road's down here, and they cut up through put a giant road cut through the Galena Platteville, and you see the nice bedding, and that's nice, but we see, you look at the side and you see a lot of springs coming out or water staining. Well, if this is all one aquifer, that would never happen, right? Because you get a potentiometric surface that looks like this. But instead, we have these horizontal flow barriers, which is causing, a whole different kind of setup with the water levels, where you get kind of this series of little potentiometric surfaces as we get towards the flow. And if you look at it closely, what happened in the Galena Platte, which I thought was interesting that I didn't know until we went on that field trip, was that there's ash layers in there. They're not very thick, but they're soft. So they don't fracture. I mean, they're soft sediment, so it can fill in the fractures and stuff. So there's naturally all these ash layers which act as vertical flow barriers in there, because they don't dissolve karstically, and if there's fracturing, they don't fracture because they're soft, or don't fracture very well. So that may be a case of, well, maybe we need to divide the Galena Platteville up where there's ash layers. Nice thing about the ash layers is they're really widespread, because there's some volcanism somewhere distant that dumps a lot of ash. So, if we go to the Galena area of northwestern Illinois and try to have one Galena Platteville layer, we'd probably be in a lot of trouble, because what would happen is we would have a lot of homeowners that have lovely house and have a well up here that's full of water, and our models will never be able to reproduce that. Our models will want the one potentiometric surface that's down here.
Mm.
So dividing model layers up will depend on what questions you're trying to answer.
That's where it becomes important if we're in the driftless area in Northwest Illinois and we need that level of detail. So then we're in Joliet and maybe we need some detail but a lesser level of detail. Making sure, because anytime you add a layer, you're adding now a lot of computation if we have a statewide model. So being able to zoom in and get the appropriate level of detail in the appropriate level without carrying that everywhere is something that we're trying to work toward, and that's where I think FlowPy helps us out. Building a network of models that are all connected. It's more difficult to do when you're constrained in a GUI.
Sure.
That's a long-term vision.
Yeah, right. That makes sense. We can go in a lot more detail locally and then stitch them together with FlowPy.
I do want to point out on here for the quaternary, you'll notice all these detailed hydrostratigraphic units. That's where we have mapping that's been specifically done. You'll notice unspecified episode. That's most of the state where we don't have mapping, and we have some crude things that we've thrown into the model. So we're in the process of combining a Kane County model and a McHenry County model. We've been in the process of doing that for 4 years, I think. The Mahomet model, all those have nice mapping done by the ISGS. And
Nice
then we
mapping? Some mapping. Yeah.
some mapping. Yeah, I was thinking nice mapping. You know, McHenry I think is pretty good. Kane is pretty good.
Yeah, Kane's good.
Mahomet is in various stages of quality, I guess.
Yeah, I'll talk about that next time.
Yeah.
So it's noon, so I didn't want to drone on for hours and hours. Give people time for lunch.
Felt like 4 hours anyway. So.
Sorry about the distraction on the bedrock, but I think it's important to understand what you're modeling.
I didn't really understand it even close to that level.
Yeah, to give you a little background on the bedrock.
Did you want to say anything quickly on that report there before I turn off the webinar?
Hand that over.
Okay, great.
Congratulations.
I'll just want everything closed out.
Yeah. Cecilia, where would you like to go?